Welcome, physics students. We're going to take a look today at energy and motion. We've done some work with forces and motion, and today we're going to try to fold in the idea of energy. We're going to start with a sort of simplistic approach and then move into something a little bit more sophisticated. As you see on the screen here, we've got a ball that can roll down a ramp. Okay, it's got a mass m, it's at a height h, and in general we can say that objects in motion have two types of energy. They have a gravitational potential energy because they are in a gravitational field. They also have a kinetic energy, which is the energy due to motion of its own. We can define both. So the gravitational potential energy is the mass times the gravitational attraction, that's mg, so that's the weight of the object, or force, times the height above surface. So gravitational potential energy would equal mgh. As h shrinks, of course, as the ball is coming down the ramp, the height will get smaller and smaller. As that happens, the potential energy will diminish as well. So where does that energy go? Well, certainly one place where it goes is that the ball starts to pick up velocity, starts to pick up more and more motion, and so the kinetic energy will grow. Our formula for that is kinetic energy is equal to 1/2 mv squared. And of course, the higher the velocity, the greater the kinetic energy for any given mass. So let's take a look at this ball in three different positions here. If we imagine the original height to be h1, then the gravitational potential energy at that point will be m times g times h1. That's kind of a poorly drawn 1 there, but there it is, mgh1. And if we imagine the ball rolling down and getting to half the height, then the gravitational potential energy would of course be mg times h1 over 2. And we go to the logical conclusion here that when it gets to the ground, the gravitational potential energy would be 0 because h would be 0. But of course, at that time, it has picked up a fair amount of speed and is now moving, as this red arrow indicates, moving to the right with some velocity. So all the energy that was first trapped, if you will, inside the gravitational potential energy has now become kinetic energy. So there is this inherent trade-off. As we lose as we lose potential energy, we gain kinetic energy. And if this was a bowl and the curve came back up to the right, as the ball climbed, it would gain potential energy and lose kinetic energy. All that leads us to the following statement here. Let me just reveal this. The following statement that the total energy that the ball has is a combination of its potential energy and kinetic energy at any given moment. Okay. One specific example is if the potential energy at the top was 100, then at the halfway point, its potential energy would be 50 joules. The other 50 joules would have to be kinetic energy. And as the ball proceeds to the bottom, the potential energy would be 0 and the kinetic energy would be 100. So potential energy and kinetic energies can go up and down, but the total has to remain a constant. But we know that this is pretty simplistic because we know that eventually the ball will roll to a stop, and the implications of that are that the gravitational potential energy will equal 0. And because it comes to a stop, the kinetic energy will be equal to 0, and the question becomes, where did all the energy go? Well, we're sharp enough to think about forces, and we understand that friction plays a central role in this. And we know that this ball will move to the right and eventually come to a stop someplace out on the right here. So we can move to a more sophisticated version of our energy equation by thinking about the work done by friction. Okay. Let me hang on a second, the work done by friction, okay? It is the frictional force, whatever that happens to be, we know how to calculate that, times the distance. As each meter rolls by, as the ball rolls by meter, the work done by friction increases, and eventually all the energy that was originally wrapped up in potential energy at the top becomes a mix of potential energy and kinetic energy down the ramp, and then just purely kinetic energy on the ground. Eventually all that energy becomes thermal energy, or what we call the work done by friction. So let's take a moment to just consider a picture like this, a bowl where there's a mass that's held at a height h. We know that its potential energy, of course, would be mgh, whatever that would be. Again, let's say that that's 100 units of energy, 100 joules. Well, in a frictionless world, let me grab that. In a frictionless world, the ball would roll down, and when it got to this point, it would have 0 potential energy and 100 joules of kinetic energy. And then again, it would continue, of course, because it's got all that energy, and it's rolling up the hill, and it would eventually come to exactly the same height, and it would now have 0 kinetic energy because it would stop, and the potential energy would once again be 100 joules of energy. So in the frictionless world, this ball would continue to roll, this marble, whatever it is, would continue to roll inside this bowl and constantly roll back and forth and reach the same height over and over again. In reality, of course, there's some friction involved every step along the way, and though it's hard to calculate what it might be, say, on an angle, like at this point in its travels, the friction exists, and with every meter that the ball rolls, there's some work done by friction, and so the ball might come to a rest here at some height that's clearly not the same as the original height. So now it has less potential energy, 0 kinetic energy, and some energy has gone into work done by friction. Okay? As it rolls back, it will lose more and more friction and eventually just get to maybe here. And then as it rolls back, as it rolls back, it might just get to here, and so on, and back and forth and back and forth. And eventually, it'll settle on the bottom, 0 potential energy, 0 kinetic energy, and the entire 100 joules of energy would then have been converted into the work done by friction, which heats up the surfaces, heats up the ball, but is it not in any real sense available for the ball to use. Okay, hope that makes sense to you all, and that you understand those 3 components of total energy: potential energy, gravitational energy, and the work done by friction. Okay, take care.